Welcome to section 4.3. In this video, we're going to be talking about quadratics, graphing quadratics, vertex form, standard form, and finding maximums and minimums. This will be mostly a continuation of what we did in class on Monday and just filling in the details so that way you have it all in one place. So I think we all know what a quadratic is. It's a function that looks like f of x equals ax squared plus bx plus c, and a, b, and c are just numbers of the problem's choosing. And when we graph them, we get parabolas, and usually there's some line of symmetry. So the first form we're going to talk about is vertex form. Vertex form is when a polynomial has the form f of x equals a x minus h squared plus k. And these are very easy to graph through our graph transformations. All we have to do is, if we have a specific example, say f of x equals 2, x minus 2 squared plus 3, we can draw our graph axis. And then our usual quadratic, if it was just f of x equals x squared, would look like that. This function has been shifted to the left, or sorry, to the right by 2 units. So we go over 1, 2. And it's been shifted up by 3 units. So 1, 2, 3. So the new graph is going to look something like that, and we'll draw it stretched out just a little bit. The 2 stretches. And so that's all there is to it when it's in vertex form. We're able to easily figure out right away how it's graphed. We write it with this minus h and k, so that way our vertex is at hk. In our example here, our vertex is 2, 3. So all we have to do is just find the vertex and then stretch it by the requisite amount. We also have another form for our quadratics. These are a form you're probably used to. The f of x equals ax squared plus bx plus c. So for example, f of x equals x squared plus 2x plus 1. This is much harder to graph. We don't see it as a clear graph transformation. We can figure out the y-intercept pretty easily. Our y-intercept is just when we plug in x equals 0, implies that our f of 0 is 1, and that's our y-intercept. But that's about all we're able to get out of the graph of this. And so our way of remedying this is through a technique of converting a standard form to vertex form. So if we have a polynomial in standard form, sorry, a quadratic in standard form, ax squared plus bx plus c, our goal is to make it look like, I guess I need to use a different letter that's not a. So we'll say r x minus h squared plus k. And we can do this by just completing the square. So we'll start by just pulling an a out of the first two terms. And then we want to complete this square. So we'll get a x squared plus b over a x. And remember, we add b over 2a squared and minus b over 2a squared plus c. And now we can do a little bit more simplification, maybe fill in the details of how the simplification comes on your own. So we get a x plus b over 2a squared minus b squared over 2a, over 4a plus c. And then we set h equal to minus b over 2a. We'll set k equal to c minus b squared over 4a. And then we get that a x minus h squared plus k equals f of x. And so that's our transformation. And so when you're converting from standard to vertex form, you can either remember what h and k are, or you can just walk through the completing the square on your own. So for our example, where we had x squared plus 2x plus 1, we don't need to factor an a out this time. So we can do x squared plus 2x plus 1. Our side work, we'll take 2, divide it by 2, and square it. That just gives us 1. So we get x squared plus 2x plus 1 minus 1 plus 1. And then we know that this factors down to x squared plus 1 equals f of x. And we're able to see that the vertex occurs at -1, 0. And yeah, maybe you saw from right with x squared plus 2x plus 1 that is just x plus 1 squared all along. We didn't really need to go through the adding and subtracting 1. But it's always good to be sure what you're doing is correct. And so once we do that, we can easily graph it, where it's +1, so that just says that our parabola got shifted to the left 1 unit. And so our graph looks like this. All right, and we can also use quadratics to solve maximization and minimization problems. So let's say we have a company, ShakeSmart, wants to determine how they should price their smoothies in order to maximize revenue. In section 4.2, we talked about data analysis and finding lines of best fit. So let's say they sent someone out to study how the amount of smoothies they sell varies with price. And their line of best fit ended up being 100 minus 10x. So they're going to use that as their model, that if they price their smoothies at X, then they will sell 100 minus 10X smoothies. Maybe we can think about why that equation makes sense. So that says when X is 0, they're going to sell 100 smoothies. So basically there's at most 100 people even want a smoothie. So if they're free, they'll get rid of 100 smoothies. But that's probably not optimal in order to maximize their revenue. And if they price their smoothies at $10, then they sell 100 minus 100 smoothies. So they sell no smoothies at all. There's not one person who's willing to buy a smoothie at $10. So our goal is to figure out what price should they actually put for their smoothies to maximize revenue. So revenue is just price times quantity. And so we'll call that R of X equals our price is X and our quantity sold is 100 minus 10X. So that's telling us how much revenue we get when we set the price at X. And if we distribute that X in, we get the quadratic minus 10X squared plus 100X. All right, now we want to find the minimum, which we know is going to be that vertex of the graph. So what we're going to do is start with minus 10x squared plus 100x and just walk through completing the square. So we'll factor out this negative 10 and we get x squared minus 10x. Now we want to add and subtract. So that way we can turn this into a square. So we take 10, divide it in half, that's negative 5, and square it. So that tells us that we get 25 minus 25 and now we can distribute this 10 to pull that 25 out. So we get minus 10 x squared minus 10x plus 25 plus 250. And then that front factors as x minus 5 squared plus 250. So that's our vertex form. And our vertex is at 5, 250. So our graph looks something like this, where at 10 and at 0, at 5, we're up here at 250. And it's a parabola, so it's going to look something like that. We're at 5, we hit the most for our revenue, which is 250. And we also know that it has roots at 0 and 10, because if it's 10, we sell no smoothies, so we don't bring in anything. And at 0, we were giving away our smoothies for free, so we don't bring in anything. But so the ideal price is 5. If we charged more than 5, well, we would make more money per smoothie. There wouldn't be a lot of people who want to buy smoothies. So we would end up around here. If we charged less than 5, we'd be selling a lot of smoothies, but not bringing in as much. So we'd be around here. So that's how we can determine that we should price our smoothies at $5. All right, so that's maximization. All right, see you around in the following videos.